students, welcome to the EN 401 lecture on buckling. Here's the roadmap for our lecture. We're going to talk about some terminology, then buckling failure, and then we're going to talk about the critical buckling load, which involves finding the effective length, the slenderness ratio, looking at the slenderness ratio transition, and then the critical stress and load. And once we figured all that out, we will go ahead and talk about and calculate factor of safety. All right, so some terminology, structural terminology. So we're going to talk about columns mostly in this lecture. So a column is a vertical structural member that carries loads from above down into the ground or the foundation. All right, so we've got a bridge here, and the bridge has these large beams on top with cars on top of that, right? So all this weight from this bridge gets carried into these columns, these big 4 white columns, and those columns transfer that weight into the ground and the foundation system. Over here on the right, we have a steel building going up, and we have some columns here, and in between the columns are beams, and eventually things will be spanned across the beams, and all that weight will get carried in the columns down to the ground. So some other names for columns are pillar, post, pole. You've probably heard of some of those things and maybe some more. The main role of those columns is to carry the loads and to also support those horizontal structural members, which are called beams. So buckling failure is a form of deformation as a result of an axial compressive force. And so we see these axial compressive forces typically in our columns, our structural columns. So when we get buckling, we end up getting a massive amount of bending due to the column's inability to withstand that axial compressive load, right? So axial compressive. So right here we have a picture that shows 2 things. So this dotted line would be the column prior to the buckling load being applied, and then this buckling load P is applied, and our column or our strut bends out in this deformed shape. So buckling is always a sudden failure. Oftentimes there's no initial signs of failure. It just kind of happens very quickly. And so the reason we get this sudden failure is due to the mathematical relationship between P and Y. So P is the buckling load, or just the load placed on top, and Y is the amount of lateral deformation of the column. So we get this lateral deformation because essentially X starts getting shorter, right? This point starts moving down this way. So as this moves down, Y begins to increase, right? So our bending moment due to buckling would be P times Y, and as Y increases, so does the bending moment. So you end up getting this cyclical increase in buckling or bending moment because they both just continue to increase, right? So bending moment increases, and the more this goes down, the more Y increases. So it's a big cycle, and you get a catastrophic failure from buckling. So here's a bunch of videos and pictures of some different types of buckling failures. So this pole vault here is interesting. So it's not quite buckling failure. You know, the thing doesn't break, but it does buckle. But then it rebounds and launches the pole vaulter over the bar. Here's a couple of videos, some Coke cans buckling, and then here's a photo of a column that buckled, and you can see that that sideways bending instability here. You can see that we had an axial load coming straight down, and then we got some bending. The load that causes a column to buckle is called the critical buckling load. And we are able to calculate that critical buckling load with these factors that we have shown here. So if we know the length of the column, the type of end conditions or connections that the column has, the geometric stiffness or moment of inertia, which we have just covered, the material properties in the cross-sectional area, we can use all that to calculate what our critical buckling load is. And the importance of calculating the critical buckling load is you want to compare that to your design load, what you think the building's going to be loaded with, and make sure that the column is strong enough to withstand the loads that the building or structure are designed for. So the first thing we're going to look at for calculating the critical buckling load is the effective length. All right, so those first two were conditions that we saw on that slide were length and end connections. So if we combine those two pieces, we can calculate what's called the effective length. So the effective length is equal to K times L. All right, so L is just the length of the column, and K is the effective length factor, which is dictated by the end conditions. So we have this chart here that shows us what our end conditions, with different end conditions, and what our K value is. So if we're fixed, our K value is 0.5, fixed pinned 0.7, pinned 1, pinned free is 2. Right, so lower K values are better. We like our columns to be short. Shorter is better in columns and buckling. So now we know how to calculate the effective length. We'll look at the next piece that helps dictate column buckling, and that's the slenderness ratio. So the slenderness ratio is related to our geometric stiffness or our moment of inertia. So the way we calculate our slenderness ratio. So slenderness ratio is equal to our effective length, so K times L, divided by our radius of gyration. So the radius of gyration is related to that moment of inertia. So here's our equation for radius of gyration. It's equal to the square root of moment of inertia, Ix, divided by the area. The radius of gyration is different about the X and Y axis of our column. So you'll have to pick the smallest value so that you get the highest slenderness ratio to do your column analysis. Right, we're looking for worst case scenario, so you always want to find your smallest value of R, so whether it's Rx or Ry, so that you can find the highest value of slenderness ratio. And once you find our slenderness ratio, we can classify our column. We can either classify it as short, so short is going to be our strongest column, so slenderness ratio less than 10. Intermediate would be a slenderness ratio between 10 and C sub C, the critical slenderness ratio. Right, and our long and slender columns have a slenderness ratio greater than that critical slenderness ratio, which we'll show you here in the next few slides. So this graph here shows us the critical buckling stress of A36 steel columns based on their slenderness ratio. Right, so our slenderness ratio is here on the x-axis, and critical buckling stress just for A36 steel columns here on the y-axis. Right, and so we notice that where slenderness ratio is less than 10, our critical buckling stress is going to equal to our yield stress. And then as our slenderness ratio begins to increase, our critical stress, or the amount of stress required to cause buckling in our column, begins to decrease. Right, so it decreases along this red Johnson parabola line until we hit this point here. So this point here is C sub C, or the critical slenderness ratio. For A36 steel, it's about 126. Here's the calculation for that. So you can calculate that exact number if you'd like. So it's about 126. So at about 126 slenderness ratio, we jump off the Johnson parabola and we jump onto this Euler equation parabola here, this blue line here. So you can see that the blue line and red line, are different equations, right? So we get different lines. But above C sub C, we're going to use this Euler equation, and we can see that our critical stress continues to decrease with an increase in slenderness ratio. So long, tall, slender columns have a significantly lower critical stress that would cause buckling as compared to short columns, right? So if our slenderness ratio is out here at about 240, we're down to a critical stress of about 5,000 psi. So 7 times less than if that column were to be considered short. So the next slides are going to show us how to calculate the exact critical stress based on the slenderness ratio. Here's some examples before we get to some of the equations. All right, so to find the critical stress, right, we need to know what the slenderness ratio is, and we also need to know what the material type is. All right, so here's all the things that impact our critical stress right here. So we have 3 different equations. As we saw, we had that 3 different zones of slenderness ratio. We had that short columns, intermediate columns, and tall and slender columns, and we saw that all those had different equations to determine what the critical stress was. And so we have those equations written here. So if we find our slenderness ratio is less than 10, we have a short column, right? So we say that our critical stress is equal to the yield stress. So that's a pretty easy one there. If we find that, let's say we're just working with A36 steel to make life easy with numbers. So let's say our slenderness ratio is greater than 10 but less than 126, because 126 is the critical slenderness ratio for A36 steel. Then we would be an intermediate column here, and you could calculate the critical stress with our slenderness ratio, KL over R, remember that's our slenderness ratio, divided by this, right? So this factor here will give you something less than 1, which is multiplied times the yield strength. So some factor less than the yield strength would be our new critical stress for intermediate columns. And if we end up with a long and slender column, so for A36 steel, if we are above C sub C of 126, this would be the equation that we use. Note that we have Young's modulus here in the numerator, so that would be 29 times 10 to the 6 for A36 steel. That's in PSI. Slenderness ratio here in the denominator, so you don't have to go ahead and plug this in. You've already solved for this to get to this point. So that'll give you the critical stress, and this critical stress is what would cause that column to buckle. And once we have the critical stress, we can then find the critical force, which is just the critical stress times the cross-sectional area. Now that we've calculated our critical load, we want to calculate what's called the factor of safety. So the factor of safety describes how much stronger our structural member either needs to be or is as compared to the design load, or what is actually going to hold, right? A lot of building codes dictate what factors of safety need to be for different types of structural members, whether they be columns, beams, dams, foundations, you name it, there is a factor of safety requirement for each of those in the code. And so the way we figure out if our column is designed properly is we will calculate the critical load that would cause buckling, right? So we calculate that critical load that would cause buckling, right? So that's irrespective of how the building is designed. This is just that one piece, what force will cause that to buckle, right? And then we divide that by what our actual or our design load is supposed to be, right? So perhaps we design our column to hold 2,000 pounds, right? So this could be 2,000 pounds here, And let's say we actually figure out that it only needs to hold 1,500 pounds, right? So we could calculate that factor of safety. So 2,000 divided by 1,500. That would give you your factor of safety. And we're always looking for a factor of safety greater than 1. So our factor of safety is greater than 1. That means our structural member is not going to, or is not expected to fail with the loads that will be applied to it. If our factor of safety is directly equal to 1, that means failure is imminent. So things could go either way. So it's not prudent to calculate or to design something with the factor of safety 1. Yes, it'll hold, but that leaves you no wiggle room for any extenuating circumstances, and you end up with a very dangerous situation. And if your factor of safety is less than 1, then your column or whatever it is that you designed will fail. So you've designed your column to be less strong than it actually needs to be. So let's say we designed our column to that 2,000 pounds, but actually we need to put 3,000 pounds on there. So that would give us a factor of safety less than 1, which means we're going to have some failure. So here's some examples down here, and the answer should be on the slides in the bottom. All right, here's example 1 for calculating the critical buckling load and stress. Go ahead and give this a shot and take a look at the example video once you get it complete. All right, and here is the review. So why do columns buckle? From axial loads that cause column instability. How do end connections impact a column's ability to resist buckling? So by changing the end connections, you can vastly change the strength of a column, right? Because that changes the effective length, and we know that lower effective lengths make for stronger columns. The slenderness ratio allows you to classify your column between short, intermediate, and long and slender, right? And remember, we always want to pick the higher slenderness ratio, so we need to analyze both the slenderness ratio for the x and y axis, and that calculation is KL over R. The difference between critical load and calculated load. So critical load is what load will cause the column to buckle, and the calculated or actual load is what we're actually going to put on there. So we always want to make our column stronger than it needs to be so that it doesn't fail. And what is the minimum factor of safety that does not lead to failure? And that is 1, right? If we calculate a value of 1 or greater, it's not going to fail. Less than 1, it will definitely fail. Thanks for watching.